So we've had the preamble. And the preamble will actually be useful for the next talk as well, the second part. But, okay, so what do people do? So we've got the problem. We've outlined the situation, the process. So this is what other people are doing, kind of stuff. So here we've got a whole group of birds. I don't know a great deal about birds. So global families of birds. I have seen videos. The rest of them are just Latin names to me mostly. So what it is this group of birds lives all around the world, and the various species live in various places in the world. So what they do is divide the world up into regions, and one could spend days, I could probably spend weeks discussing how things are divided into regions. But basically we've got species that live in the A area, which is Madagascar. We've got another group of species that live in B, Central Asia, Southeast Asia. Then we've got some that are in Africa, and we've got some that are in other places. Basically, they map out which areas a species are found in. Then they run a simulation algorithm and various complex Bayesian models. Has anybody heard of Bayesian statistics? All right, okay, that's something to do. Go look up Bayesian statistics. They run these incredibly complicated models based on evolutionary theory to try and reconstruct the most likely group places that the ancestors lived in. So that's what people do. And they include, so this is an example of the model, the sort of processes that are being modeled by these algorithms. So different algorithms model different processes. So some of them allow dispersal, some allow extinction, some allow sympatric divergence, species in the same place diverging into two species set by things like sexual selection, vicariance, which is the diversification by a geographical barrier forming and splitting a species. That's called vicariance. Founder effects, long distance dispersal, they build up various parameters of these complex statistical models, which frankly are beyond I understand the basics of how they work, but the mathematics of it is not my area. So they build these complex models, and they try and run these models across these things to try and find the most likely history in relation to those areas. Great, I thought, let's do that for Mexican fish. Oh, there's my thingy going wrong. Okay, so I'm fighting, as you can see, I'm having an ongoing war with corruption of some of the text on my slides. Anyway, so what I thought I'd do is, okay, let's make a model of how the areas change through time in Mexico. So I decided to build a space-time composite area model. Remember time and the lectures on time? One of the data models was a space-time composite in which you take one layer and you basically divide the area, the layer constantly to get all permutations of combinations of areas through history, and then you recombine the areas, you dissolve the areas back together to reconstruct a particular time. So I tried to do that. So I had a data model that basically consists of a set of polygons, the composite polygons, the world split into various polygons, and then I have each. So what I want is historical catchments, a basement in time, and those are made up of many of these polygons, these split polygons, and the split polygons are recombined in lots of different ways to give different basins through time. That was the theory. And of course, this relationship consists of the end-to-end relationship. We have it gets turned into a table which says has the catchment ID in a particular time period and the ID of the polygons, one row for each of the polygons that make up that catchment at a particular time. So I got this far. So this is central Mexico. Basically, I've split whenever I thought there was I got information, and I'll talk about the data about where historical watersheds were and things like that. I split the modern basins up and started chopping them into smaller areas based on where the historic basins were. This area in here, I also included the lake systems in here like this. You're not familiar with the geography, and here are my 3 tables. I've got my geography catchment table. These are all these 131 polygons. These are grouped using the MEX area catchment table. So these are the areas here, the area IDs, and they together form catchment 1. Catchment 1 is called the Snake River, which is dated to the mid-Miocene with a time period of start of 14, which is 14 million years before present, and it came to an end roughly 13 million before present. So that was the data model that I tried to build to then run these area-based mathematical reconstructions using it. It seemed so simple, but it was a complete dead end. Why was it a dead end? Well, it was just impossible to do. So we knew where the main paleo channels were. There were some maps, the maps produced by the water engineer, but they were only the main channels and the ones he'd happened to find. And there were no watersheds indicated on that map. It was just where the channels. The watershed is the division between the basins. So we didn't know the extent of the basin. We just knew where the main rivers ran. So there was uncertainty in the channels, that information. We didn't know the type of basin change necessarily that occurred. We maybe know that there was some kind of change, but we didn't know whether it was a vicariant event, a splitting event, or a piracy event, a river capture event. There's huge uncertainty in the time of any events that we know about, and I'll talk a bit more about events in due course, and the paleo channel maps. It wasn't really clear how we incorporated the lake systems into our area-based model. And I trying to guess where old watersheds were from a digital elevation model, building Thyssen polygons around channels to estimate paleo drainages. But frankly, it was on hiding to nothing. It was hopeful rather than meaningful, I think. So, and finally, despite the fact that's just 3 tables, it's actually an incredibly complex data model, that space-time composite model, to manage manually without maintaining spatial and temporal constraints on the polygons, the relationship between the polygons. So it was a right pain to manage. So not only was it really, the data was not sufficient to be able to do what I was trying to do, it was also quite difficult to manage it computationally as well. So at this point, life is a bit tricky. You had an idea, you thought, yeah, this is new, this is interesting, we can do this. The reality is, no, sorry, 6 months down the line, this isn't going to work. So we've got a problem. Area-based models, they require a fully defined area connectivity history model to work. So we need a full model of the geography of the areas, and then we try and match the evolutionary trees onto this history of areas. But we can't define a fully connected one because the information is missing. It's difficult, it's impossible to do. So we are unable to define the model due to partial information on past hydrology. Trouble. So what are the solutions? Well, here are 2 solutions. One is just to say, okay, the information we've got on past hydrology is surely only a small amount of what exists out there. Can we get better hydrological reconstructions through the synthesis of other data? So basically go on a data hunt, see what we can find, especially given the newly available digital data, high resolution terrain models from satellite imagery, other data sets, increasing availability of biological data sets, evolutionary trees, digital geological maps. So can we bring this information together in one place to improve our reconstructions of the landscape history? Or can we take an alternative tack and look for statistical relationships between environmental drivers rather than trying to actually at a micro level reconstruct exactly what happened in the past, say this is overall what happened in the past. So two approaches, and I'm going to explain these two approaches briefly. Firstly, reconstructing hydrological change. So there's lots of information in the literature on maps about events that have changed the hydrological connectivity and character in the air in central Mexico. So it would say a river capture event happened here in roughly 1 million years ago, we think, and this is the evidence for it, if you're lucky. So, but one of the problems we have, of course, if we go back to the time lecture, is that the pattern events in the past create pattern in the landscape, but through time that pattern is eroded and fragments as the additional volcanoes explode and dump a kilometre of lava on top of the evidence, for example, or it's eroded away by high levels of erosion. Or perhaps simply no human being has gone out looking for this stuff wherever it is in the landscape. So there's a whole reason why evidence is minimal. Nevertheless, there was a lot of information out there we could start to bring in. So went on a massive literature review looking for the various bits of evidence in the geological, biological literature that exist. I've been searching for additional evidence in newly available data sets, and with an attempt to synthesize the evidence to confirm or refute events and infer the spatial location and the timing of events. So this is the kind of thing that I'm trying to do. So this is a river pirate, remember a river capture event, it's also called river piracy. So the stream used to, this was the old watershed in brackets, in dashed, the stream used to run through like that. Then something happened, this stream eroded into this channel, captured the upper part of the river, and it now flows this direction. What evidence is there in the landscape that allows us to say that this kind of thing happened? Well, there's a variety of things we can look for. One of the biggest is what's called the elbow of capture, a sudden change in direction of your stream, indicating that a capture event may have happened. Of course, sudden changes in direction of streams can also occur for other reasons, not just river capture. But there's other evidence here as well. So the channel used to flow through here, so there's often what's called a wind gap, basically a fossil valley that the stream never doesn't flow through anymore. So there's basically what's called a wind gap, a valley in the watershed that often has fluvial sediments in it, river sediments in it, because the river used to flow through there. So that's good evidence that the stream used to go through there. We also get misfit stream on the other side. Because this used to be a much bigger river and it's lost a whole load of its water, it's a small river in a big valley. There is also, the eroding stream. These pirating streams are mostly erosive, highly erosive, so they tend to be in gorges and chasms downstream, so that it's showing their erosion. Also, as they erode, so we've got a stream coming down like this, we've got the other stream with a steeper gradient, it erodes into the stream, and you get what's called a nick point, a change in the longitudinal gradient of the stream. So and of course the taxa that lived on it, the species that lived on it, if there was a species that lived on this side, here, that got split, we might end up with one species, sister species here, and another sister species there. So if we take all that evidence together, we can start to say, once we've got one piece of evidence, it's not clear that this is what's happened. But once you've got 3 and 4 bits of evidence for the same event, you can be reasonably certain that a river capture event occurred. So that's what I'm trying to do. Here's another example. This is another thing, this is like Zirawan. We have a stream, and in this case, we've got a volcanic eruption that blocks the stream, so we don't have a wind gap, we don't have fluvial sediments. Well, the fluvial sediments and the wind gap are basically buried under a huge lava flow, but we do have a lava flow potentially there. We maybe got an overflow slipway in that this old watershed was eventually overtopped by a lake system, and then the water started flowing down that system. So we've got a different set of characteristics for perhaps a lava-blocked event from a capture, sort of river erosive event. So what I'm trying to do is to collate all the geological, biological evidence that I can get to decide whether which events happened, where and when. So information sources. So the planar river network will give me, I can look for sharp bends, elbows of capture. Longitudinal stream profiles, the downstream profile of the stream, I can look for nick points. Geological maps give me eruptions, eruptive strata. They also give me fluvial lake sediments and faults, because rivers tend to exploit lines of weakness in the landscape and will tend to run along faults rather than elsewhere, just to complicate life. Digital elevation model gives me a high-resolution river network and basin topology, or it helps improve my river network and basin topology. Also use it for looking for these erosive gorges and wind gaps and low watersheds which may have been breached in the past. We've got these paleohydrology maps, historical lakes and river channels. I've got my species distributions. I've got my evolutionary trees, which allow me to identify areas where disjunctions, where sister species are far apart from each other, which allows us to infer or guess the mode of speciation, whether they were speciated in the same place or they were geographically isolated. And then there's lots of individual textual descriptions in the literature which isn't necessarily explicitly geographical. So one of the first things I had to do was I need to measure the bends and I need to measure the long sections of the rivers and things like that. So what I did was I built myself a modern hydrological network model for central Mexico, and as far as I'm aware, it's the most detailed, fully connected model for the area. So I've got a 90-meter shuttle radar topography mission digital elevation model, and I've got 125,000 stream network maps where they've digitized the streams off paper maps from Conabio. Conabio is the Mexican equivalent of the Environment Agency in English, sort of nature rolled into one. So this was a hugely complicated operation. I mean, this took me probably a good 1.5 to 2 years to do. Basically, it involved editing the basin polygons to conform to, so having the polygons for the basin extents to conform to the 90-meter DEM. So I created, so from a sort of regional scale model of basins, I created a highly detailed local model of basins. Had to do things like, so the river lines digitized on the maps, they digitized the banks of the river. So we had to digitize center lines for where they digitized the two banks rather than a center line, so there was lots of that. The maps that we had dams and irrigation channels, so lots of human-based stuff on. We had to delete all that, remove it from the layer. There were various places where channels were missing because they hadn't been drawn onto the map, maybe because they've been covered up by agriculture or something like that, difficult to know. So where missing information was, used Google Earth imagery and actually sort of traced the missing bits of stream network from the Google imagery. And then once I got a rough model, I had to turn it into so I've got basically a network of lines, but I need to now get the flow on the lines. So I need to know how high the ends of each lines are. So I get the ends of the lines, the elevation of the ends of the lines from the digital terrain model. Then we model flow as flowing downhill from the higher to the lower end of the line. And in theory, that should have worked well, and it did work for probably 90% of the map. But in other cases, for various reasons, and basically because there's a mismatch between the terrain model and the stream lines, some upstream lines were actually higher from the DEM than the downstream lines. So it was then a whole other sequence of adjusting building the network model. So now this was the point where I was going to show you the network model. Unfortunately, the problem is I can't now shut this down without all the thingy going on the thing. So we'll leave that for the moment, and if I have time at the end, I'll show you that at the end. But this is the high resolution basin model that I created. Inside this, we've got a high resolution network model. And as I say, we'll show that later rather than stopping things. So I've got a stream network. A geometric vector model is a geometric network in ArcGIS, which allows me to trace flow up and down these rivers. So that's great. So I can use that to look for, so I've now got a good functioning planar network, and I can look and I can search for these bends and things like that. But I'm also interested in these long sections so that I can look for these nick points. So I identify 14 sections along, or stretches along interesting sections of river associated with one of these events, these 30-odd events that I discovered. So this is a sort of a schematic of a little bit of the network model that I've got. So I've got so what I need to do is, so if I had it's not just a long, a single line that I'm interested in a number of sub-channels as well. It's basically a river network, and I'm picking up the main channels. So it's not just a long profile along one line, it's a long profile along a tree structure, a dendritic tree, just like it's an evolutionary tree, but this is a tree of river networks in space. So it's like this. So I have a profile number, so I have a number of profiles. Each profile is made up of a number of sub-profiles, which are basically the lengths of the vector lengths. So these are the nodes. This is a line. This is a line here. And we need to know, for each sub-profile, we need to know the down ID of the profile. So this is number one. Profile. They're all part of profile one. This is sub-profile one. Because it's this part of the river. A sub-profile is a part of a river, and the down ID is 0 in that this is the mouth of the river here. Or this one, sub-profile 2, or this one, sub-profile 2, would extend potentially up here, further up here, and we've got the down ID is the profile ID of the downstream one, similar to that. Okay, so to calculate the long sections, I extract elevation at the vertices of the line. So these are the end nodes. So along here, we've got lots of vertices as well along the lines. So I extract the elevation from the DTM at the vertices of the line. Great. But there's a problem. Because the streamlines were digitized from a paper map, not from the terrain model, derived from the terrain model, there is a mismatch at the local scale between the terrain model, between the streamlines and the terrain model, as in the streamline is not always at the bottom of the valley, especially in gorges where you've got winding gorges, narrow gorges, the streamlines could be up the side of the gorge. So elevation does not always descend downstream. Well, that's not good. So what I did is I extracted all my river profile data out of ArcGIS, which is where I got the vertices data, into the statistics program R, which is where I tend to do some of this kind of stuff. So for each stream line, I calculated the cumulative distance upstream from the most downstream node in each project, so in each profile. So basically, this is our river. We start, so that's 0 here, and we're measuring the distance of all these nodes and vertices up the tree from the bottom. But we want elevation of the stream, so that's giving us distance along the river, but we also want the elevation at each of those points. But remember, because of the mismatch between the streams, we've kind of got a scatter of elevations like that. And so what I did was I calculated the minimum downstream elevation from the top downstream. So we always took the minimum elevation and draw the profile like that, which means it always goes down. So it's a cumulative minimum down through that set of points to get the profile, to estimate the profile. And then we plot them. Well, we don't. Okay. So this is the River Lerma in the main river that drains the southern part of the plain. This is my profile. As you can see, this is my profile in purple, and you can see it's a profile that involves multiple streams, basically a profile of the entire river, the main channels of the entire river, and you can see it goes way up here. Here, these symbols here are the various geomorphological features and other interesting information that I extracted from the literature and other maps that is all to do with these geomorphological signatures of things that happened to the river system in the past. So things like incised channels, where's the faults, old watersheds that have been marked on maps, places where you have narrow valleys, river bends. So this one, the triangles are these places where potentially we've got these sharp bends which may be linked to river capture. Look at this one up here. The main channel goes woof like that round in a bend. That's the kind of signature that we're looking for. Okay, so that's sort of the overview of the mapped information that I have. These crosses are low watersheds. Low watersheds connectivity can change due to tectonic change, volcanic eruptions very quickly. So it's collating all the information onto the maps. And then we can place that, run those profiles. So this is the long profile, here's the mouth, and we can take the profiles of the rivers, the river system, and we can plot the vertical location of these various features, geomorphological features, onto the long profiles as well. So for example, here's a river bend. Now, is there any nick point associated with that river bend? And the nick point should be somewhere at the bend or upstream. And we're looking for a change, a noticeable change in slope of the river channel. There isn't anything obvious there. There isn't anything obvious there. And there isn't anything particularly obvious there. Now, maybe it's just the scale at which I'm working. Maybe it's the quality of the data. Maybe the nick point has just eroded itself out. They erode out eventually. But we've also got lots of other information. We've got the position of the Miocene, Paleo lakes, modern lakes. We can see these flat areas. These are probably dams. So this is the surface here represents the surface of the water rather than the actual land surface. We've got areas where we've got faults crossing, etc., etc. I'm not going to go into the details of it, but that's how I'm looking at for these nick points and how these whether these geomorphological features in the geography match onto changes in slope in the long profiles of the rivers. Here's a specific example, back to good old Mount Colima. So here's a good story. Okay, what's your time? Here we are on the side of a stratovolcano, which is constantly erupting. Well, not constantly, but it erupts every couple of years. You get huge, what are called lahar flows, massive debris flows. Basically, the snow on top of the mountain melts. You get these huge mud debris slides that come sliding down the mountain. And it's a highly dynamic environment. So here, this is in fact one species of fish called Allodonthius zonistus, which is found in the Armeria catchment and in two places in the adjacent Cohoyana catchment. Okay, so it's interesting in that you've got two places just over the watershed where this species is found in this watershed, but nowhere else in that watershed. How did they get there? So I see the biological pattern, I focus in on the geology. So it's the biology that brought me here, but it's the geology that tells me what the story is. Okay, so we can see here, look at this river channel. These are flowing down the sides of the volcano here. Then we get this turn here, and then it turns down here like that. And we've got this other channel on the other side, blah, 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 turn, away it goes. Quite possible that the original channel seems very logical that this used to flow around like that through there, and then there was a blockage, a vicariant event, an explosion, an eruption, then blocked this channel, and the water then started flowing down here in this direction. And this is why, so this part, this is the old watershed, hypothesized old watershed. These fish were in this catchment. There was an explosion, blocked the channel there, and that's how they came into being this channel. So this isn't speciation in that they're the same species, but as time goes on, they will speciate. So this is capturing that speciation process in action. And if we went out and took detailed DNA analysis, we could maybe even estimate how long ago that happened. We could also look at the sediments here and take, say, carbon, potassium, argon dating to get a date as well of the eruptions here. So we've got a combination of this change in direction. We can also look at the extent of various eruptions. So here's the, this is from the geological map. The red is the extent of quaternary debris avalanches, lahars and epiclastics, basically explosive eruptions. And we can see that the area that we are is within this area of quaternary. The quaternary is roughly since the end of the last ice age. So this, well, it's Pleistocene. It goes about 2 million years, basically. So this event probably is less than 1 million years old as a result of a volcanic explosion, and that this created this change. So if we can collate this type of information for each of the possible events scattered across central Mexico, I can recreate my map. Here's my individual, here's the long section about down this river here. And it's in fact this river here. The long section comes down here and down like that. Looking for a nick point. Well, there's no, this is where this line here is where the turn in the river occurs, and there's no obvious change in slope. So there's no obvious nick point here. Also, it's interesting, you probably can't see this, but there's a scatter of points. I've also placed the points from the overlay here. And the scatter of points gives you the depth of the gorge that the river's flowing through, which I think is a really nice artifact. It's getting something for free for something not working very well in the past. So the long profiles are not as good as they could have been, perhaps, but the scatter gives me the depth of the gorges on either side, which I think is a wonderful little artifact and it's freebie. So what I'm doing is I'm trying to collate all this information to create regional type maps like this, which reconstruct where new watersheds formed, where old watersheds existed, and where the changing in flow happened. So here, for example, it used to be that this part of the Panoco Basin used to flow down here into the Lerma Basin, but this watershed, the present day watershed, formed through whatever process that happened, and the water that was used to flow that way now flows that way down to the Atlantic. So I'm creating these regional maps, and if anybody's looking for a project, I'm looking to, so this is a rough start. It doesn't have the individual information on the geomorphological things, the sediments, the 90-degree bends. I would love somebody to make us a digital or a paper or a large AO map, cartography, that showed all this information in one space. And that could potentially be a dissertation project if anybody's interested in mapping paleo river channels in Mexico. Also, paleo lakes. So the lake system, so one thing that I did was look at the slopes. So it's highly questionable how large these lakes were. Some of them were, so this is approximately 1,000 miles long, this is a humongous lake, potentially. Other people don't believe that this was ever one lake and that it might have been a series of sub-lakes. We also know that slowly through time, this big lake, or lots of lakes separate, slowly sort of evaporated, and is presently, there's a remnant lake called Lake Chapala, which is still quite large, like 90 kilometers long. That's the remainder of this huge lake system that existed in the past. But we don't know exactly when it existed, we don't know exactly how extensive it was. But if we map the flat areas, so this is the slope, we can see that this large extent of the estimate of the paleo lake extent matches very well into the flat areas of the map. And maybe that's just the criteria that was used to draw it by the water engineer, by de Cerna. However, we can also look at, from the geological map, we can look at various lake deposits and things like that. And we can see that the lake deposits actually also are not bad. I mean, clearly they're not, there's no clear pattern, but they roughly match to the extent of the lakes, the large lake system. So we're undubious about the length, size, and the age of the lake. So annoying. Okay, so that was the summary. Basically, in the process of trying to reconstruct as much as possible the history of the area. Okay, so we know. So the next one I'm going to do in about 3 minutes or 5 minutes. Okay, so the alternative I've approached is a statistical pattern approach. So instead of thinking about hydrology, because we've got so much problem with hydrology, we don't know what's happening where, is let's ignore hydrology and let's go to, which is the proximate cause. The proximate cause is just the thing that causes something. But the thing that causes the thing that causes something, in this case, is volcanism and tectonics. That's ultimately what's driving it. So the fact is we've got pretty limited information on hydrology. What information have we got on volcanics and tectonics, and can we use that? Here's a hypothesis. So here's the hypothesis that we work on. If volcanism drives divergence, then we'd expect a negative correlation between volcanism and range overlap. So basically, where you've got no volcanism, low volcanism, basically there's a background rate of diversification of vicariance. Remember, vicariance produces ranges that are not in the same place, sympatric in the same place. Whereas if we've got lots of volcanism breaking apart the hydrological network, then we would expect the species that are closest related to each other to be in different places. So basically we'd expect higher or increased injunction and low overlap in areas of volcanism if volcanism is driving hydrological change, which is driving speciation. In quiet areas, lower volcanism, lower hydrological change, more overlap between species because they're more likely to have evolved in sympatry. Luckily, Luca Ferrari, geological map man, has produced maps of eruptive geological eruptions through time on the basis of potassium carbon dating. So what I did was took his maps. I built a 3D space-time model of volcanism. So basically here we're looking at 0 million years, that's the present day, 5 million years ago, 10 million years ago, 15 million years ago. The purple dots are the individual dates and locations of the eruptions dated with potassium argon dating. The polygons, these 3D polygons, are the space-time polygons that enclose these observations. And basically, in that white area, we're talking exploding volcanoes and everything else. Outside, we're talking quiet, not much volcanism going on. So, oh God, we're never going to have time to do all this. So what I need to do is to identify the space occupied by groups of species and the space between them if they're not overlapping each other. So what I need to do, or what I do, is create some things called a geophylogeny, which is a space-time model, basically taking the geography and the evolutionary tree and combining it into the single space-time model. Okay, so here's an example. Basically, I'm quite proud of this. Geophylogeny is my word. So when it gets into the Oxford English Dictionary, if it ever does, that's I'll have invented a word, which is a nice thing to have done in your life. So, basic situation, mitochondrial DNA in brown bears in Europe. We've got a tree, and these are individual bears where they were sampled. That's there. It's a very simple, just a sort of toy example. We know where the bears were sampled, and we know which bears, which tips of the trees, so these are genetic variants basically, were observed at which locations. We digitized the tree, we digitized the map, the locations of the map, the point locations. We've got this link table, which is basically a 1 tip to n relationship between the tips of the trees and the geographical locations. And then we build a space-time tree. We basically build the tree on space. We know where the observed nodes are. We know where we saw the bears and they were measured. We've got to make some kind of calculation to where we locate the internal nodes of our tree. We need some kind of way of drawing the branches between those points across the map. And then we maybe add some attributes. As we can see here, we've got a little diagram. We've got little nice 3D bears sitting on the land to make a nice pretty picture. Okay, so we do things like that. How do we locate the internal nodes? Well, there's a variety of algorithms that we can do. We can just do it on an envelope centroid. So here's our observations. These are where the bears, the tips, were observed. We just do it in the centroid of an envelope. We do the same on that tip there. Here's the tree here. And then we locate the orange node in the center of the envelope between the two nodes, these two nodes. So we can do that, or we could do it distance weighting, based on distance weighting. We could do a variety of algorithms. And while I was at Nescent, I wrote software that does this. There are also other people. These people work in rabies transmission. So this is who use diffusion models, Bayesian multi-criteria diffusion models and things like that to locate their tips and internal nodes of their trees. It's not suitable for me. But for this work, I needed to know both the space occupied by a clade, in this case the blue area or the green area here, but I also needed to know the space between them. So what I do is I build what's called so these are point observations of each species. This is the tree with the tip. So what I've done is I've built minimum convex polygons around the set of points for each taxa. And then as we move up to the next, the higher node, we build a minimum convex polygon around both sets of points, and we do that all the way up the tree, building these MCPs all the way up the tree. Then when we've got these MCPs all the way up the tree, then we look at how they overlap. So in this case, two species, A and B, closely related to each other. They're disjunct, they're in different locations. And the space between the MCP, so this is the MCP basically of the parent minus the MCP of the two daughter species. This D is the disjunction area, the space between the two species ranges. Here we've got overlap, we've got an overlapping area, and then we've got two species, and then the other thing we can get is one enclosed within another. So these are the spatial relationships between the two clades. That's a node. I appreciate this probably hurts your head sometimes. This is what it looks like in reality. Two examples here, two groups, two species. This one here, the overlapping area between these two species is here. The more overlap, the more likely it is to they evolved in the same place together. These two species are separated, this orange zone. This is the space between those two ranges. This is quite likely to be vicariant because they're separate. This is, of course, all the evidence that goes with it that underlies the thing. So, disjunct or low overlap is likely to be vicariant. High overlap, potentially evolution, say in a lake, sympatric evolution in a lake. How do you actually see? So I've done this for that evolutionary tree of all the things. And the question is, how do you actually see this incredibly complex information? So I spent probably 2 weeks or at least drawing some complex diagram like this, which is suitable for a presentation in a publication. But really, this is what we're looking at. This is that 3D. So this is the, so the lines here, okay, it looks like spaghetti, are the evolutionary trees colored by the different types. We've got the river systems here. We've got the individual records of species, and then we've got the tree further up here. The orange is the disjunct, the areas, the spaces between sister species. So look here, or sister clades. So this is the space that separates the yellow one from everybody else. The green is the area of overlap between them. So this is, remember the 3D, this is using elevation to represent time, and these are all lines that are located in 3D space-time. And then we take these overlap and disjunction polygons, intersect them with the volcanism, the space-time volcanism polygons, to work out how much of each of these overlap or disjunction areas is volcanic at that time. I'm just going to plow on because I think we might finish. So, and when we plot this out, so this is age and this is overlap. These are potentially vicariant splits. These are in the same place, and we can see that we get lots of disjunct ranges, basically with no overlap, indicating that being split by some kind of barrier is likely to be an important mode of speciation all the way through the time. Notice we have this big gap here where a lot goes on, seemingly. Then we get a whole load here with relatively high overlap. So we've got lots with no overlap, very few with low overlap, and a few more with higher overlap. So we've got a pattern. If we plot out those potential vicariance events over the map, and here's the Paleo Lake system, what we see is most of these events are basically, we've got a plateau, and then we've basically got a steep slope, and they're all to do with sort of things falling off the plateau, basically. So we can see that, for example, this here, that's the Mount Colima event here. We've got a disjunction that's going that way. Here we've got disjunctions going that way, that way, that way. If we plot the orientation of the disjunctions, we can see the vast majority of them are in 1/4. They're all going sort of this way. They share the same direction. There's a few that go that way, most go this way. And this is, I think, linked to the geological large-scale tectonic changes and patterns of volcanism, but I won't go into that right now. So we map these patterns of disjunction. So this is the patterns of differences between ranges. And if we can plot the northing, the midpoint of those polygons against the latitude through time, we see that these disjunctions are moving south through time, and the lava, we believe that the plate that is underneath the continental plate or the oceanic plate that's broken off and is underneath Mexico, which is melting and producing these volcanoes, is also moving south. So the biology is matching the large-scale geological pattern. If we look at overlap, we can see there's the modern Lake Chapala, here's the Paleo Lake, and we can see this is the number of overlapping polygons, and it's concentrated on the present lake, and it extends out roughly the extent of the estimated Paleo Lake system. Also really interesting, there's a parasite of these fish, which is these black dots, and they are all found along the outskirts, the potential margin of this Paleo Lake system existed, say, 1 million years ago, and the distribution of this parasite apparently is still the same as it was roughly 1 million years ago, and there's also other fish that show that pattern as well. So finally, we revisit the hypothesis. Basically, we're looking for a negative correlation between overlap and volcanism, and depending 2 different ways, including the disjunct ranges and discluding the disjunct ranges, both give a significant linear relationship. Basically, you get more overlap with less volcanism. Sorry, you get greater overlap the less volcanism you have. Less overlap, the more volcanism that goes on. So, conclusions. Science. Limitation in hydrological reconstructions limit the ability of model-based techniques. So can't use the stuff that everybody else is using. We've got the vicariants all along the margins of the plateau. We've got sympatry within the Paleo lake system. And so we've got diversification appears to be driven both by volcanism and the Paleo lake. There's no one answer, it's several things, different things going on in different places. And we've got this correlation between volcanism and divergence basically moving south through time. Data management issues. Okay, we've got diverse evidence that's now collected in one database. When I say one database, it's in fact in one map file which connects to multiple data sets spread all across disorganized across my disk. So it needs a good tidy up. It's unwieldy, as I say. We've got multiple GIS databases, shape files. It's not consistently organized. No formal metadata collected. So I started collecting this data up to 10 years ago. And now I have to try and remember what I did 10 years ago. I wish I'd collected a lot more metadata. So these geophylogenies are using the geometry Z value to locate and display the information. These these aren't easy to edit manually if you decide you want to edit the tree in some form or fashion. We also basically need I need a topological, space-time topological model for building alternative basin connectivity histories that I can then pump through to the sort of these sophisticated analytical techniques. And just a little bit on visualizing the spatial temporal pattern can be really difficult and time consuming. I've tried 3D space-time, as you've seen. I've built animations. I've made static figures. They all take a lot of time and effort to produce. It's very difficult to know exactly what to show. Lots of occlusion problems. We haven't even started on uncertainty in this information. So these diagrams, quite a lot of them, they have a high wow factor, but they're actually can be difficult to understand if you don't have a good insight into what you're actually looking at. And it's for explanation in journals and indeed your presentations, a simple graphic is often better than a super wishy-washy thing or a super whiz-bang thing. And the interaction has been really important in developing this. The ability to point and click and look at the data in 3D, look at it in 2D, has been a huge advantage. And there you go. Have a good holiday. And I hope you found that interesting. And you can at least, I think it's very interesting to listen to other people's applications and what they've done and the problems they have. You probably will never, unlikely to have evolutionary problems, but you'll face some of these issues along the way, potentially in what you do. And you learn, you learn by looking at what other people have done and learning how to. All right, so thanks.